Welcome back. So, we are basically discussing several strategies for a given target molecule based on transformation based approach, starting material and substrate based approach. Talked about many transformations. Today, we are going to discuss about some unusual transformations, and but let us first formulate what is the target structure given to you. I am saying I will give you a target molecule whose structure is this. This is basically a methyl group, the stereo center was not specified. You are having a CH2, CH2, 2 CH2, then you are having a alkyne functionality, CH2, CH2 alkyne. This is a target molecule. The starting material was given to you. The starting material was given to you. The starting material was a bicyclic compound, this one starting material. Okay. Now, if you count the number of carbon for target molecules 1, 2, 3, 4, 5, 6, the rest of the part is remain same. So, this is also 6 member. So, only thing is from this starting material to target, this particular bond, not this, basically the cleavage usually takes place here, You get a carbon oxygen bond and a alkyne was generated here, remaining part remains same. Now, here I will try to first talk about a reaction or a transformation which is named as Eschenmoser-Tanabe fragmentation. This is the key reaction which we will be using in our discussion for solving this problem. Now, this I am not sure whether all of you know this fragmentation, but it is a very unique transformation. Probably it is not given in many textbooks, but we first discuss it. Now, I will draw a structure and to explain what exactly this reaction is. This reaction is basically fragmentation of epoxy tosyl hydrazone. I am taking a epoxide something like this, okay, and then I am reacting with a tosyl hydrazine. What is tosyl hydrazine? This one, tosyl group, as all of us know, is a paramethyl SO2 group, this group, and this is NH2, sorry, NH2. So, initially this carbonyl group reacts with this to give you a hydrazone. So, it gives a NH SO2 phenyl, this phenyl is basically paratolulyl. Okay. Then your rest part is similar, methyl, all the methyl remain same and a ethyl. So, I have just taken a epoxide, substituted epoxide to show how this reaction takes place, it is a fragmentation reaction. Now, the condition is this compound is now next subjected to any base, suitable base, butyl lithium. Now, if you see this butyl lithium, we will try to abstract this particular hydrogen, which seems to be very much acidic due to presence of this nitrogen as well as this sulfone group by electron withdrawing. So, fine. So, this will be abstracted and you will then get this minus and this S double bond O and let us say tolulyl means 4 methyl phenyl. The remaining part is all similar. You have a ethyl group here, you have a methyl group here. So, after the initial base abstraction you are here. Now, this nitrogen won't sit idle. This nitrogen will try to delocalize this negative charge, and if you see we have a electrophilic epoxide oxygen which can accept this electron flow. So, flow will be something like this, and this epoxide basically will be open, epoxide will be open, and what essentially you will get, you will basically get a product. This double bond is now will be created here, okay, and then you will get this end, this ethyl group will now here, and this epoxide as it is open up, you will get a O minus, you get a methyl, you get a methyl, fine, and then you will get a N double bond N, N double bond N from this, and then you have this S double bond O and toluene group, S double bond O and toluene group. So, this was the main thing. Now, next step is very interesting. Next step, I will just first write it what is the next step will happening. As you are having a O minus at one end, this O minus also is not a very stable species. So, what is try to do? You will try to fragment the molecule in this way. Now, this sigma bond will be now has to break and put a triple bond here, okay, and then this basically forces to give a nitrogen species to expel, and then this entire sulfonyl things will also leave. So, it is a very interesting reaction, and then finally, what will be happen? We will again draw the entire structure as in the earlier intermediate, then we explain how it takes place. So, this is your thing. So, as I said, the fragmentation takes place like this, like this, like this, like this, and finally, what you get? You basically get from this part, this bond is going to be chopped down. You basically get acetone. Acetone is this, you get acetone, okay, and then you are getting a alkyne here. So, alkyne means you are basically getting Et, and then you are getting a nitrogen as a gas, and then you are also getting this toluene sulfonyl thing, probably as a OH minus. So, the entire thing is a unique fragmentation reaction, which will basically give you a alkyne as a main compound. Now, if you go back to the initial starting material, what we have initially drawn to explain the reaction mechanism, the starting material is this. After the fragmentation, what it gives? It basically gives a alkyne and a acetone. So, basically you get a PHC CET, you get a triple bond here, and this entire part is basically fragmented out as acetone. So, this was the main reaction. Now, in coming to present context, we have to see what is the target molecule and what was the main thing. Now, see the target molecule. The target molecule I am again drawing it from you, drawing it for you. The target molecule is basically a cyclohexanone based compound, this one. The starting material was given to you a bicyclic ketone. this one. So, this reaction is basically nothing, you need to use a intramolecular version of Eschenmoser fragmentation. So, first what you need to do, you need to prepare the epoxide. Now, here is a very useful reaction, how you can make epoxide of an electron deficient bond. This bond is linked with a carbonyl compound. So, it is electron deficient oxygen bond, and MCPBA, the reagent for epoxidation of your olefinic double bond, is also electron deficient. So, how a electron deficient reagent can react to a electron deficient olefin? In principle, it is very difficult. Okay. So, in this case you are using a nucleophilic oxidizing agent, and usually this is not an oxidizing agent, it works in a different way. If you use hydrogen peroxide with sodium hydroxide, you are basically generating a hydroperoxide anion, and this hydroperoxide anion basically attacks in a Michael fashion here to give you, probably all of you know it, but still I am explaining it. Basically it will come here, then it comes here, and basically you get a O minus. So, O minus backfires, then this things comes attack here, and you get the corresponding epoxide. Now, so epoxide we need because we have to do a intramolecular Eschenmoser fragmentation. Now, subject this compound to react with tosyl hydrazine NH2, and you will basically get a double bond NTS, the epoxide is here. Okay. So, the mechanism basically now goes in similar way, and only thing is you basically fragment this part out of this thing, out of this molecule, and the fragmentation takes place, you generate this ketone, and this end will be your alkyne, So, now you get this ketone from this epoxide thing. Epoxide acts as the electron sink, it can receive the electron which was initially generated at this NHTS at this end. This methyl group remains here, and then you get this as a alkyne. This alkyne is the main product. So, until and unless you know this Eschenmoser fragmentation or Eschenmoser-Tanabe fragmentation, this whole problem will be very difficult to solve. That is what I am telling this. You need to know couple of very interesting transformation, and this Eschenmoser-Tanabe fragmentation is one of the transformation which you can think of using it through a series of similar kind of reaction, but the reactions are very compact. You take a ketone, alpha beta unsaturated ketone, make the corresponding epoxide through a nucleophilic mechanism. Okay, as I said, hydrogen peroxide NaOH, then make the tosyl hydrazone and then do the fragmentation. That is exactly what we do here. So, we will from single transformation to multiple transformation, that is basically we are doing. Now, in the next problem we will try to figure it out if a multiple transformation based strategies and how it solves one of the problem which we will be dealing next. The target molecule next which I am giving is this compound. I say this pyrocyclic compound, 6 member ring, 6 to the cyclobutanone, 6 and 4 member ring. Okay. The target molecule. Now, in principle you can solve it through many pathways. The transformation which we will be now pointing out is basically known to you. It's basically known to you. The transformation is basically named as Meinwald rearrangement. Meinwald rearrangement. Now, how it happens? Probably all of you know. As I said, if you have this kind of epoxide compound which is unsymmetrical, in the retro quiz we solved this Meinwald rearrangement puzzle by using a symmetrical epoxide. Now, say this epoxide we are subjecting it to Lewis acid. It will have completely different pathway than the symmetrical epoxide, but initially the coordination is there. It is fine. The oxygen is now basically little bit polarized, that makes carbon oxygen bond to open it up, and eventually the choice of carbonium ion formation, it is very important. You might have a choice that this carbonium ion is forming as one case. In other case, you also have the possibility to form another carbonium ion by opening through this way, and in this case you will basically forming this carbonium ion. So, both the carbonium ion in principle can generate, but in reality this will be the most stable carbonium ion. Why? This secondary carbonium ion, this is also secondary, but this carbonium ion is basically having a cyclopropyl thing attached to it. Now, cyclopropyls are basically equivalent to a vinylic system, because due to the pi character in the cyclopropane ring. In reality, cyclopropane ring does not have a pi bond, but cyclopropane, if you check the hybridization, is a very strained molecule. In reality, it should have a 109 degree bond angle as standard sp3 hybridization demands, but cyclopropyl ring, to make it a 3 carbon unit, the bonds are normally kind of a deformed. It is basically always having this kind of banana bond to give you this cyclopropane system. This is the real cyclopropane picture, and as why this cyclopropane, the substantial pi character in it, it is like a vinylic system. That is why cyclopropyl carbonium ion is equivalent to vinylic carbonium ion, which is absolutely not stable. So, this carbonium ion won't be stable, you would be having this carbonium ion. So, fine. Now, this carbonium ion we will now try to rearrange within this molecular framework, and find a 1-2 migration will basically takes place like the way pinacol rearrangement takes place. So, this one of the cyclopropyl will migrate, because cyclopropyl system is strain system. The strain releasing factor in the cyclopropane system is the governing factor. Then once it migrates, it will basically give you a 1 carbon extension, okay, and then you will find these things. So, now the Lewis acid can go out from this reaction mixture, and you will basically get this as a main product. So, this is basically nothing but a systematic exploration of a pinacol type of rearrangement. Eventually, if you are not familiar with this Meinwald rearrangement, you can do it in different way, but okay, our next process will be how to access this epoxide, because this epoxide is also you require. So, next our target will be to access this epoxide, which is now required for the Meinwald rearrangement to access the target. Now, accessing this epoxide will be using a reaction again for a single step transformation, is a FGI based reaction. Now, this transformation is named as Corey-Chaykovsky reaction or Corey-Chaykovsky transformation. I will write it. Corey is the E.J. Corey, the famous E.J. Corey-Chaykovsky. Corey-Chaykovsky reaction. Now, what exactly this reaction is? This reaction is very interesting reaction. Corey-Chaykovsky reaction you can search in the scene archive. Scene archive, you can just go and search in the scene archive, you will find some nice link. In reality, this reaction is basically you take a carbonyl compound and react with this kind of sulfonium iodide. This sulfonium iodide can be generated by reacting with dimethyl sulfite Me2S and methyl iodide. Now, eventually what happens if you take this sulfonium iodide reacting with a base, you basically have a anion generated from one of these methyl, okay. And then this methyl attacks to this electrophilic carbonyl, it becomes O minus. Now, this O minus now basically initially get this O minus CH2 S plus methyl. Now, this O minus now attack intramolecular SN2 fashion to this carbon sulfur bond to release this dimethyl sulfite and will give you a epoxide. This is a one way of epoxide synthesis through exploration of Corey-Chaykovsky reaction. Now, here we will be using a similar kind of Corey-Chaykovsky reaction if you having a sulfur based reagent which is commercially available. Anyway, nevertheless, if you are not familiar with Corey-Chaykovsky reaction, that also you can do. So, you take this compound, react with a base. Now, this compound on reacting with base, put a minus here, S plus PH2 BF4 minus, cyclohexanone is here, okay. So, minus comes here, go, this O minus when backfires it attacks to the sulfur, okay. To make it more simple, I will write it O minus, then is your cyclopropyl thing, and then S plus PH2. So, now this O minus attacks here and get rid of this diphenyl sulfite, you get the corresponding epoxy species. Now, this epoxy species you have to use it in this Meinwald rearrangement. As I said, eventually if you are not familiar with this Corey-Chaykovsky reaction, you can still do it, you take this cyclohexyl thing, you can do a Wittig reaction by taking this cyclopropyl bromide reacting with this triphenyl phosphine to get the corresponding P plus PH3 Br minus. So, the Wittig salt, okay. Then next you react this Wittig salt with the cyclohexanone to get the corresponding, this is very simple, okay. Now, these things you can next react with MCPBA, that will give you this epoxide. So, this is one way you can get the epoxide, fine. There are other ways, you can, if you do a dihydroxylation reaction, that also will give you the target molecule through a pinacol rearrangement. So, now you do a pinacol rearrangement. Remember the retro quiz, we talked about pinacol rearrangement, okay. So, first the most stable carbonium ion will be generated here. So, initially you will basically generate a carbonium ion here, this OH and these things. Now, 1,2 migration will takes place. This 1,2 migration will basically takes place, this 1,2 migration, and this 1,2 migration will basically give you a 4 member ring. Ring expanded things with a OH and is positive. Now, this will lose the H plus to give you the desired target molecule. So, now you check entire pathway, there are independent OS we have explained. So, we said you have a starting material, just trying to recapitulate the whole thing. Starting material, the product which was desired is something like this. So, I said route 1, we have talked about Corey-Chaykovsky reaction plus Meinwald rearrangement. That was one of the nice way, and if you know both the reaction you can explore it, and in the way you learned a new reaction called Corey-Chaykovsky reaction. Route 2, you do a Wittig reaction with this corresponding triphenyl phosphine based cyclopentane based halide and then a Meinwald rearrangement. Route 3, you do a Wittig, then you do a osmium tetroxide mediated dihydroxylation, and then you do a pinacol rearrangement. So, in principle all these 3 pathway you can basically try, but probably this reaction Corey-Chaykovsky reaction was not known to you. If you know the Corey-Chaykovsky reaction, then basically you can design this 3 pathway. If your supervisor or if your teacher asks this problem, you can basically design 3 different pathway, provided that you know this Corey-Chaykovsky reaction. If you do not know, do not worry, you pick up this Wittig reaction pathway or Wittig as well as osmium tetroxide mediated dihydroxylation pathway, and then pinacol. So, as I said, the choice is yours, but you have to pen down many suitably or logically driven approaches, and out of that, depending on your resources, depending on the steps, depending on the yields, you can choose the best possible pathways. So, that should be your main approach, and next week also we will try to discuss further more strategies, more problems, more transformation. Till then, have a good time. Goodbye.